Hello and welcome to Mass Academy. I am Noor Alam. I am extremely happy with my friends, students who are watching these videos, and they for the long time they asked me to make a video like that in one short video about the topic circle. So now in this video I am going to make one short video of the circle, which is divided into the two part. First part of the video is the theoretical part, and the second part of the video is the problem solving part. So first of all, in short, we coming to know the definition of the circle. So circle is defined as a locus of a point which moves in such a way so that its distance from the fixed point is always fixed. So if we have a point like this P which moves in such a way so that its distance from a fixed point is always fixed, then the locus of the point is known as the circle. So this point we consider as the fixed point, and this point O is the fixed point, and this point P is the moving point. This point P is the moving point. Okay, now moving point. This point O is the fixed point. Fixed point. So now this moving point has the coordinates, suppose x comma y, and the fixed point having the coordinates a comma b. All of you know that when you joined the moving points and this fixed point, this distance is known as the radius. So now I am going to apply here the distance formula, and so that if OP is equal to the radius r, so from here we got OP square is equal to r square. Then OP square is nothing but x minus a whole square, and this is y minus b whole square, which is equal to r square. So this is the equation of a circle with center. This is the equation of a circle with center a comma b, and radius is r, and radius is r. And suppose if what will happen if the center is 0 comma 0. So if center is 0 comma 0, then what will be the equation of the circle? Okay, here one thing you should notice that this is equation 1, where we have this is equation 1, this is equation 1. Okay, now this is okay. So this is equation 1. We call this is our equation 1, where we have the center of the circle a comma b and the radius is r. There, so the equation will be x minus a whole square plus y minus b whole square equal to r square. So now suppose that if the center is 0 comma 0, then what will be the changes in the equation? Just you put here in the place of a is 0, in the place of b is 0, then you are getting nothing but x square plus y square, which is equal to the radius square. So now this is the second form, where the center of the circle is origin and the radius is r. Then what will be the equation of the circle? What will be the equation of the circle? The equation of the circle will be like this. Okay, now so this is our equation 2. I think all of you clear up to these steps, there will be no doubt. And all of you know that general equation of a circle we are going to calculate. General equation of a circle. So now in case of a general equation of a circle, first of all we from the one what we get, so one gives equation 1 gives x square, and then I have y square, then minus 2ax, then minus 2by, and then we have the constant term a square, b square, and minus r square. This is I am calling this one is the equation 1. After expansion what we got, this one I called the equation 3. So this one I called equation 3. This one I called equation 3. Okay, this is our equation 3. So this is 3. Now consider the equation x square plus y square plus 2gx plus 2fy and plus c. If I write the equation 3 in the form of equation 4, if I write the equation 3, listen carefully, if I want to write the equation 3 in the form of equation 4, equation 3 I am going to write in the form of equation 4. So can we say that what is the value of G, F and C? So everyone can identify the coefficient of x is 2a, here the coefficient of x is 2g, so therefore 2g is equal to 2a, so we can write g is equal to minus a, or from here you are getting a is equal to minus g. Similarly you are getting after a you are getting that is b is equal to minus f, and then you have what, c is equal to a square plus b square and minus r square. So from here you can calculate r square will be equal to a square plus b square and minus c. So now a square value, you know, a value is minus g, so it will be a value is minus g, so g square plus f square minus c. So from here we get the radius, which is equal to root over of g square plus f square minus c. So what we observe that if you are going to write the equation 3 in the form of equation 4, that is known as the general equation of the circle. This is known as GS, general equation of the circle. So now general equation GE, we can write this one as GE of circle, GE, general equation of circle, GEC. Okay, now so now general equation of a circle, which is x square plus y square plus 2gx plus 2fy plus c. This is the general equation of the circle, very important form. So this will imply the center of this circle is nothing but minus g comma minus f, and after center you are getting the radius also. The radius is equal to root over of g square plus f square and then minus c. So listen carefully. When the equation of the circle is given to you and you are going to calculate the center, what you have to do, you divide the coefficient of x by 2. What is left, you take that value with sign change. Divide the coefficient of 2fy by 2, that means coefficient of y, that is 2f divided by 2. Whatever you are getting, take the sign change, do the sign change. That will be the center of the circle. Now after that, radius you very can easily find out, the square of the sum of the center's coordinate minus of c. So this will be the center of the circle. Now here what we have discussed in the definition 1 of the circle, and this is the general equation of the circle, that is our point 2, general equation of the circle. Now coming to the general second degree equation. When does general second degree equation gives the equation of the circle? So do you know the general second degree equation? General second degree equation look like this: ax square plus 2hxy plus by square plus 2gx plus 2fy and plus c is equal to 0. So this is known as general second degree equation, general second degree equation, general second degree equation. So this general second degree equation, does it represent the equation of the circle, general second degree equation? So answer is yes. If the coefficient of x square, so if the coefficient of x square is equal to the coefficient of y square, number 1, and coefficient of x into y is equal to 0. So if it is happened simultaneously, then you can say that the second degree equation always gives the circle. But here also remember, the coefficient of x square should be equal to the coefficient of y square, but it not necessarily be the 1. It may be the any number, 2, 2, 3, 3, 4, 4, whatever the number, but both the coefficient should be the same. And coefficient of xy is 0, that means they want to say that h value should be 0. So if it is happened, then you are always getting the equation of the circle. Okay, now so if you look at the equation of the circle, that is the general form, this one. So if you look at it, if you look at this general form, so you notice that here note, we can write as note. So here you can find that G, F, C, these are independent arbitrary constant. These are 3 independent arbitrary constant. So as a result, when you are going to calculate the equation of the circle, in that situation you notice that either in the questions they will give you the either 3 tangents they will give you, 3 tangents, or they will give in the questions 3 points, 3 non-collinear points, 3 points which are non-collinear, so that you can identify the circle. Or sometime they will give the 2 tangents and 1 point, plus 1 point they have given to you, so that you can easily find out the equation of the circle. Okay na, uniquely. So to determine the circle uniquely we need that conditions, so that you can find out G, F and C. So to find out the three quantities, independent arbitrary constant, we have to find, so we need the 3 equations. So these 3 equations either in the form of the tangents, or 2 tangents 1 point, or 3 non-collinear points they will give, so that we can find the equation of the circle uniquely. So now here, from here we can say that we, in the case of the circle, we chase only about the center and radius, we chase only about these 2 points, center and radius, to calculate the circle uniquely. To find the circle uniquely we required these 2 things. I hope all of you clear about this. Now, like a quadratic equation, we have the nature of the roots. Here we also have the nature of the circle. So now nature of the circle, from where we get, now this is our 4 number points. So here I am taking nature of the circle. First of all, this general equation of the circle, x square plus y square plus 2gx plus 2fy plus c. This equation represents circle, there is no doubt. And the radius is nothing but root over of g square plus f square and minus c. Center of the circle is root minus g minus f. So now 3 cases will happen. Case number 1, if this under root quantity g square f square, which is acts like the discriminant in case of the quadratic equation, that same things will happen here. If it is greater than 0, it will imply our radius is finite. It will imply radius is finite. So we can easily find the unique circle. We can find the circle is with finite radius. So radius is finite and we get a finite circle. We get a circle with finite radius. Okay, now we get a circle. So now you can write in this way, circle with a finite radius. This language will be more comfortable. Here we should write circle, we get a circle with a finite radius. So here we have circle with finite radius. Here we have a circle with finite radius. Now second things, if g square plus f square minus c, this quantity is 0, then what will happen? We have a point circle. So now consider one point circle. Here. Now we have here point circle. Suppose one example I am taking, x minus 1 whole square plus y minus 2 whole square, which is equal to 0. So this is a point circle. That means this coordinate, this point 1 comma 2, which is a dot, that will be the circle with the radius 0. So this is the center of your circle. This is actually the circle and the radius is 0 here. So we get a point circle. Now case 3 will happen if the square root quantity, the quantity which is under the root g square f square minus c, that is the radius, if it is less than 0, so no real circle we have actually the imaginary circle. So this imaginary circle we have. But you notice that one thing, here the center of the circle is real. We have an imaginary circle with center minus g minus f, but radius is imaginary and radius is imaginary radius. Okay, now so we always chase for the center and radius to get the equation of the circle. Again I repeat these lines again. So we chase for the radius and the center to find out the equation of the circle. So up to the point 4, do you have any doubt? You can ask. So nature of the circles that I have discussed in the point number 4, it is nothing but just like the discriminant in case of the quadratic equation. So here the discriminant is g square f square minus c. So if g square plus f square minus c is greater than 0, then your circle is real. You have a circle with a finite radius. Now if g square plus f square minus c is equal to 0, then you have a circle with radius 0, you have a circle that is the point circle, and the point, the coordinates of the point, that is the dot is the circle with the radius 0. If you have g square plus f square minus c, j square plus f square minus c less than 0, then you have an imaginary circle where the center of the circle is real minus g minus f, but the radius of the circle is imaginary. So I hope all of you understand this concept. So in the point number 1, I gave the definition of the circle as a locus. A point moves in a plane such that its distance from the fixed point is always fixed. Then this the locus, that is the path traced out by the moving point. Locus is nothing but path traced out by the moving point is known as the circle. Now here we apply the distance formula and we have calculated the equation of the circle. Now what will happen if the center of the circle is the origin? Then what will happen? Now how the general second degree equation, when the general second degree equation will give the circle that condition, you have to remember that coefficient of x square and coefficient of y square should be the same, but not necessarily the 1, and the coefficient of xy, that is h, should be the 0. If these two conditions satisfy simultaneously, then we get the equation of the circle. And next point we are describing that there are the 3 arbitrary independent arbitrary constants. So 3 conditions is required to calculate GFC, or in the question sometimes the 3 tangents are given, or the 3 vertices are given, or 3 non-collinear points are given, or 2 tangents 1 point are given, so that we can find out the equation of that circle uniquely. And the nature of the circle is nothing but we have to impose the condition on the radius, and radius is of the circle is in the second degree equation is g square plus f square minus c is equal minus c. So we impose the 3 condition on it and we have to check it. Now the next point is point number 5, where we are going to discuss about the diametrical form of the circle. Okay, now this is known as diametrical form. What is actually diametrical form? In case of a circle, the diameter is given. In case of a circle, now we draw the circle also from here. So now we have this circle. Okay, now so in case of a circle, what we see that the diameter of the circle is given. So now suppose this is the diameter and 2 ends are given. One is A, other is B. Coordinate of A is x1 y1, coordinate of B is x2 y2, and we are taking any arbitrary points here. Any arbitrary points P I am taking here, so that when I joined with A and P like this, and I am joining this P with B like this. Okay, now so here I want to use the different color. It will be look like this one, and here I am using the another color, this one. Okay, now all of you know that this part. Okay, now okay, so all of you know that this angle will be the 90 degree, because angle in the semicircle is 90 degree. So if it is 90 degree, that means we want to say that the slope m of the line AP and the product of the slope of the line PB must be -1. Yes. So now we take any point on the circle P with coordinate x comma y. So I have the 2 coordinates. Very easily I can calculate their slope by using the slope formula. And here I have this one xy, x2, y2. So now y minus y2 divided by x minus x2, and these also be equal to -1. After multiplying, we collect all the terms in one side, so it will be x minus x1, then we have x minus x2, plus we have y minus y1, and then we have y minus y2, and the total result is 0. and this will be the quadratic equation with roots x1 and x2. Here quadratic equation with roots with roots with roots y2 with roots y1 y2 with roots y1 using the same color pen. This one I want to use y1 and which color actually I'm using here, this one, y1 and y2 with the roots y1 and y2. So now I want to express this result as the quadratic equation. Now it is x square minus sum of the roots x1 x2 into the variable plus product of the roots. Here I want to use this one, that y square minus sum of the roots y1 plus y2 into y, and then product of the roots, that is y1 and y2, which is equal to 0. So what we know that it is a quadratic equation with the roots are given. So diametric form, this diametrically form this diametrically form this form, and here we have one more form, this one. We can use the color, change the color also. I think basic saves graphs. Okay, color we can't change, I think. Okay, now here this one also. Okay, so these two are actually same. One is the diametrical form, and this diametrical form I write in the form of a quadratic equation, because sometime in the JEE mains questions we find that they are giving the sum of the root is given like that, product of the root, and then they mixed up the questions, they form the questions like that. So when we solve the problem, then we will observe that what is the actually the problem happens, how they set the questions. Okay, now so our next issue is we are going to find intercept made by the circle. So this will be the point number 6, intercept made by the circle, intercept made by the circle. So now what is actually it, intercept made by the circle? Suppose we have one circle like this one, and one line is there. This line is actually the x-axis, and it will intersect your circle at two different points. Okay, so this will be like this one. So it intersect your circle at the point, suppose a x-axis at the point B, and this coordinate is nothing but x1 comma 0, and here you have x2 comma 0, x1 comma 0, and then you have x2 comma 0. We have to rub it this one. So here we have x1 comma 0, and another point is x2 comma 0. This is our x-axis. So here on the x-axis, intercept is nothing but this AB. This AB length is the intercept. So now we are going to calculate what is the length of AB. This one we are going to calculate. That means you can say that x1 minus x2. This part we are going to calculate. So now here we know that if I use the formula, we can write this one is same as x1 minus x2 whole square. So this will be nothing but x1 plus x2 whole square minus 4 times of x1 x2. Here I am using the algebraic formula, but the problem is here we have to know what is the x1 and x2. Since we are able to find out x1 and x2, that's why I am using here x1 and x2. So first of all, consider the general equation of the circle x square plus y square plus 2gx and plus 2fy plus c equal to 0. Now this general equation, here the circle cuts the x-axis. That means here y coordinate is 0, where it cuts the x-axis. That means actually at the point A and B. So for the point A and B, we put y equal to 0. So it will be what, x square plus we have 2gx plus c is equal to 0. So now this is a quadratic equation. It has two roots. My one root is x1, other root is x2. So from here I can find sum of the roots, which is x1 plus x2. So sum of the root is minus 2g, and the product of the roots x1 x2 is nothing but c, product of the roots is c only. So now AB length I can calculate as AB, putting the value here, so I have 4g square and then minus 4c. So if I take 4 outside, it will be 2 root over of g square minus c. Since we have one quantity under the square root, now again the tricks that we used in the case of the quadratic equation in Sridhar Acharya's formula, that technique I am going to apply here. That technique I am going to apply here, that what will happen to this part. Condition number 1, suppose g square greater than c, then your line, then your circle cuts the x-axis, then your circle cuts the x-axis at two different points. That means situation will be like this, your circle cutting at two distinct points. Okay, now so this will happen. Now what will happen if this will happen, this thing, suppose g square minus c is 0, that means g square is exactly c. So in that situation your circle must touches the x-axis. So it is our circle, and this circle actually touches the x-axis. So x-axis is like this one. So now we can say that these things will happen. Suppose if you are taking here, it is touching. Now what will be the meaning of this one? If g square minus c less than 0, or you can say that g square is lesser than c. So now your circle never cut the x-axis or never touch the x-axis. So circle will be either upside or below the x-axis. So that means the circle never cutting or touching the x-axis. Okay, now so these things will happen. Now same things we apply for the y coordinate. So if we have a circle here, and consider the y-axis is here like that, and suppose that it cuts your y-axis at the 2 point. One point is here, that is C, and one point is here, that is D. Now your target is calculate the y-intercept. So y-intercept means what? CD length. Y-intercept, you are going to calculate y-intercept, which is nothing but CD. And CD, if you consider this point is 0 comma y1, and this point you are considering 0 comma y2, so you are actually calculating the length y1 minus y2 modulus, so which is nothing but root over of y1 plus y2 whole square. Then you can write as 4 y1 y2. So now just before what we have, that here we have minus 2g, and c here you will get minus 2f and c. So what we will have 4f square minus 4c in the similar argument. Okay, now no need to worry about it, you can easily solve it. So since we have here f square minus c, so something we have in the square root sign, so we have to focus on the three quantities, three reasons will come here, three conditions will come here. So first is f square is greater than c, so f minus c greater than 0, so it will imply that y-axis is intersected by the circle at the two different point. Now if it is happened like that, f square is equal to c, then in that situation, suppose this is a circle and this is the y-axis, so that means circle is touching the y-axis. So now what will happen if f square minus c less than 0, that means f square less than c. So in that case the circle is entirely lies above the x-axis or below the x-axis, above, right of the y-axis or left of the y-axis. So in that case, so if we have this one that neither touching or cutting the y-axis, so here or here it will be like that. So hope all of you understand this concept of interceptions. Now next point is, after point number 6 we have to go for the point number 7. So here I am going to discuss, in this case I am going to discuss position of a point with respect to a circle. Position of a point, here our target is position of a point with respect to a circle, position of a point with respect to a circle I am going to discuss. So suppose I am taking here my circle is like this one, and one point is there. Suppose you can say like that point will be here. Okay, now point will be here. Suppose point is here. So this point P, whose coordinate is x1 comma y1. Now we are interested, then how can we find the condition that P is lying outside of the circle or on the circle or inside the circle. So here we have the center of the circle like this one, and if you try to connect them, so we are getting the line segment like O to P. Just going here, O to P. Okay. So now this is O, this point is the P, so we have OP. And here you notice that this length, up to this length, if you say Q, so OQ is the radius. So from here we can easily say that our OP length, from here we want to say that OP length greater than radius. There is no doubt about this, without, this is just observation. P is here lying the outside of the circle, so without any problem we can say these things. Okay, now so now we can also write as OP square. OP square is greater than radius square, but we know the value of radius square is g square plus f square and then minus c. OP square is nothing but if you take the center as minus g minus f, because we are considering position of a circle for this circle x square y square, general form 2gx and plus 2fy and plus c is equal to 0. We are taking this one. So now here you have to calculate the distance. So now distance is x1 plus of g whole square plus y1 plus f whole square. These things is there. Okay. So now what we have, x1 square plus 2x1g plus g square. Now here we have y1 square 2f y1 plus f square, and which is greater than g square plus f square minus c. So g square f square, g square f square we can cancel out. So what we have actually, x1 square plus 2x1g plus 2f1. I think you have to write first y1 square so that it looks better. x1 square then y1 square, x1 square plus y1 square plus 2g x1 plus 2f y1. Then this minus c will take on the left hand side, it will be the plus c and greater than 0. So it is nothing but s1. So if s1 is greater than 0, that means p is outside. P is outside. Okay, now so if s1 equal to 0, then p is on the circle. If s1 is less than 0, p is inside the circle. So where p actually lies depend on the s1 sign. So if sign is positive, then outside, sign is equal to 0, then it is inside, and the sign is less than 0, then it is under the inside the circle. Okay, now so these three conditions are there for the position of a point. Okay, now our next point is how can we find the parametric equation of a circle. So this is my 8th point. Now here I am going to calculate parametric form of a circle. Parametric form of a circle. So we know the standard form of a circle. From there we are going to calculate the parametric form. So I am taking one circle whose center I know. I am taking one circle. Okay, now so now here this is my coordinate axis. Okay, now this is the coordinate axis. Okay, this is the coordinate axis, like that. Okay, now so here you notice that these are the coordinate axis, and with respect to coordinate axis I have the coordinate of the center, which is x1 y1, coordinate of the center, which is x1 point and y1 point. Okay, now and on the circle I am taking any point is p, whose coordinate is x comma y. So first of all we draw OP. So we joined OP, that's I'm getting the hypotenuse or the radius of the circle. Okay na? Acha. From here if you drop one, like, you again get one radius. Now from the point P I am drawing one perpendicular on this radius, so I am getting this one. So this is I am calling M. I have a POM, P O dash M. This point I am calling O. This is our X O, X dash, Y O, Y dash. These angles supposed to be theta. So now if I apply the distance formula here, so I can write as x minus x1 whole square plus of y minus y1 whole square, which is equal to the radius square. X minus x1 whole square plus y minus y1 whole square equal to the radius square. So these things I am going to replace by r cos theta. These things I am going to replace by r cos theta. Okay, and these things I am going to replace by r sin theta. So if you write in this way, so their square will generate the right hand side r square. Is it clear or not? So that means I am taking x minus x1. Simply I am taking x minus x1 is r cos theta. So from here I am getting x equal to the center of the circle x1 plus radius and then cos theta. Okay na? Here also y minus y1. So y minus y1 I am taking r sin theta. From here I am getting y is equal to y1 plus r sin theta. So here you notice that r is the constant and theta is the variable. So in this case r is constant and theta is the variable quantity. Theta is variable. Now theta can take the value 0, lesser than equal to theta, lesser than 2 pi. So this is the range of the value theta. So now what we have, we can say that this is the general point on this circle x1 plus r cos theta, comma y1 plus r sin theta. So this is the general point for the circle, and this point is able to form all the points on the circle. That's why it is known as the parametric form. So it is a general point on the circle. So this is parametric. So here theta is the parameter. It is parametric form. Here theta is the parameter. Everything depends on theta. For the different points you are getting the different, for different values of theta you are getting different points. Okay now instead of x square plus y square, instead of x square plus y square plus 2 plus if the center is not x1 y1, actually center is 0 0 origin, then what will happen? So if the equation of the circle is x square plus y square is equal to the radius square, so in that case we should write our center is the origin. So general point will be like that, x1 plus x1 is actually 0, so x cos theta plus y sin theta you can write. Okay now? So here the radius is r and your coordinates of the center of the circle is 0 comma 0, so point will be x is equal to r cos theta. So you directly write as, no need to write again x. Okay na? So you simply write in the different form or in the point form, you can write x is equal to just like r cos theta. Okay na? And y is equal to r sin theta. So now this will be the parameter theta, and here r cos theta comma r sin theta. So this has the power to generate all the points on the circle. So this is the general point. It is a general point on this circle. So you can say that it is a general point on the circle. General point on the circle. Okay now next is equation of tangent drawn to a circle in various form. So our next topic is subtopic is point number 9. equation of tangents, equation of tangents in different form, equation of tangents to the circle in different form, in different form. The first form is known as the Cartesian form. So now here I am going to explain that if you have the general form of a circle x square plus y square plus 2gx plus 2fy plus c is equal to 0, then the tangent at the point x1 y1 of this circle is, the equation of the tangent is x into x1 plus y into y1 plus g times of x plus x1 plus f times of y plus y1, f of y plus y1. Okay, now g of x plus x1. So similarly we have plus f of y plus y1 and then constant is 0. So first our target is we want to prove these results. From where we get the results, these results from where we are getting. Okay, so now our target is first of all prove these results. So I am taking one circle here. So this is the circle and I want to one tangent. I want to draw one tangent. So our tangent will be look like this. So this is the tangent to this circle. Okay, yes. So now what we say that if we draw the if we join this point of contact with the center, if we join the point of contact with the centers of the circle, then you know what will happen, they are perpendicular to each other. So if you consider this one is the center of the circle, this point P which passes through the x1 y1 point which is on the circle, so here 190 degrees form, because you know that radius and the tangent at the point of contact, radius and tangent at the point of contacts are at 90 degree, or they are inclined at 90 degree, they form the 90 degree angles here. So can we calculate the slope of this line? It is minus g minus f coordinate. So can we calculate the slope of the line OP? So very easily, now proof of this theorem. So we have m OP. So m of OP here should be negative sign, here is also negative sign. So it will be y1 plus f divided by x1 plus g. This is the slope. So if you know the slope of this line, but the tangent, this tangent and these lines are perpendicular, so you can easily write slope of tangent. From here you can find slope of tangent. So this slope will be minus of x1 plus g divided by y1 plus f. So now the equation of the tangents I am going to calculate. Equation of the tangents. Equation of the tangent. So it will be what? Y minus y1 is equal to m, that means x1 plus g divided by y1 plus f, y minus y, this is x minus x1. Okay now, so here we have x minus x1. Okay, now do the cross multiplications. So what we have, y minus y1 multiply with y1 plus f, which is equal to minus of x1 plus g, and then multiply with x minus x1. So multiply with y1 plus yf, then y1 square, then y1f, and here we have minus x1 x1 minus gx, minus 1 is plus x1 square, then we have minus 1 is plus x1g. Okay, so now putting all the quadratic term in one side, and here I have the term x1 first, then I have y1, this is, now next is gx I am taking here, gx if you take here, now gx, and here you have y1f. Okay, yf is also there, y1f is also there. X gx you are taking here, and yf you put on the left hand side. Other term like x1 square plus y1 square, then plus x1g, then plus y1f. Any c is there? No. So now I'm writing in this way x1 plus y1. This I want to write in this way gx plus x1, and here I'm going to write f y plus y1. So you notice that here I am adding on the left hand side gx1 and fy1. So this time we should add on the right hand side also. So it will be 2 times of gx1 and 2 times of fy1. So this is very popular form. 1c is required. So now I am writing xx1 plus yy1 plus g times of x plus x1 plus f times of y plus y1, y plus y1, and then here if you add c on both sides, if you add c on both sides, so what will happen? You notice that if you are adding c here, so it will be x1 square plus y1 square plus 2gx1 plus 2fy1 plus c. So now this is what this expression says, that this expression is nothing but the value of s1. This is nothing but s1, where s is the general form. S1 means in the general form if you put x1 y1, since the x1 y1 is the point on the circle, so therefore this part is nothing but equal to 0. So RHS becomes 0. Then we have actually xx1 plus y1, and then we have g times of x plus x1 and plus f times of y plus y1 and plus c is equal to 0. So this is known as the t. This is known as t. So this is known as t. So now we can say that t is equal to 0. T is the equation of the tangent. So thus we have the equation of the tangent. Okay, this part becomes 0. So therefore equation of the tangent t is equal to x1 plus y1 plus g times of x plus x1 plus f times of y plus y1 and plus c. So this is the equation of the tangent, which is equal to 0. Now if you apply this concept in the general form, then in non-general form, in the that is in the circle, the simplest form, in that case also you can apply this formula. So before applying, you should remember some things, that when you apply or write, you are going to write the equation of the tangent in the Cartesian form. Always replace this x square, you have to replace by x times of x1. Y square you have to replace by y times of y1. X is replaced by x plus x1 by 2, and y is replaced by y into y plus y1 by 2. Okay, now, and constant, there is no change in constant. Constant will be c only. So when you have any type of quadratic form or the general second degree equation or any curve where the x square y square is present or xy present, then find the corresponding equation at the point x1 y1. You should replace x by x square, x1 y square should be replaced by y into y1, x is replaced by x plus x1, and f is replaced by y plus, f is replaced by, not f, y is replaced by y plus y1 by 2, x is replaced by x plus x1 by 2, and there will be no changes in constant. Now using this idea, can we find out the tangent for this equation at the point x1 comma y1? So answer is yes, obviously we can find. So tangent will be equal to x into x1. So our x1 point, if I am taking in the parametric form, okay. Now so now next idea I am giving, that Cartesian form is completed. Now I am going for the parametric form. So tangents for the parametric form, this is under the same point, parametric form. So you have the circle, simplest circle, x square plus y square is equal to a square, and you are taking the x is equal to r cos theta, that means radius cos theta, a cos theta point and a sin theta point. At these 2 points you are going to calculate the equation of the tangent. So these tangents will be what? Tangents will be x into x1 a cos theta plus y into y1 a sin theta, and then is which is equal to a square. So now this will be what? A cancel out, x cos theta and plus y sin theta, and which is equal to a only. So this is the parametric form of the equation of the tangent to the circle, okay. So parametric form we are easily calculate for the tangent. Now we are going to calculate the slope form. So next form for the tangent is, it is known as slope form. Suppose this line y is equal to mx plus c. This is the tangent to the circle x square plus y square is equal to radius square. Okay now, so how can we find out? What will be the conditions? Okay now, so first of all we take the intersection of these two. We are going to take the intersection of these two curves. So it is very simple, x square then y square is replaced by mx plus c whole square, and then we have the radius square. So now it is x square plus m square x square plus c square plus 2mxc and minus a square equal to 0. So from here we take m square common, it will be 1 plus x square m square, and then you have 2mc, you can say mcx plus c square minus a square, which is equal to 0. Okay now, so now this is a quadratic equation, and it is a quadratic equation in m. So we are getting the two values of m, one is the m1 and other is the m2. So since here we are find the condition that the line just touches the circle, so here what will happen, these two roots will be equal. That means discriminant must be 0. So if the discriminant is equal to 0, so our discriminant is 2mc whole square minus 4 times of 1 plus let me check something. I think if I taking m square common, so here I have, okay, let me check the calculations. Not in the x square, this quadratic is actually not correct. Quadratic, I am writing the wrong quadratic. Okay, now so for these reasons I am going to delete this one. Okay, so now okay, delete this part. Okay, now something happened which is not correct here, so I am going to take the quadratic of x square I want to make. So actually it will be 1 plus m square then x square. From here I have 2mc then x, and next you have what, c square m square, c square minus a square, which is equal to 0. So now since it is a quadratic in x, and we claim that our line touches the circle, so therefore here discriminant should be 0 of this quadratic. So this quadratic has the discriminant 0 for the equal roots. So for tangency roots are equal, so we have 2mc whole square minus 4 times of 1 plus m square and then c square minus a square, which is equal to 0, So from here 4 is cancel out, so we have m square c square minus here also cancel out, so we have c square, then we have m square c square, then minus a square, and then we have minus a square m square equal to 0. So now m square c square from here cancel out, so what we have, minus c square, which is equal to a square negative, and then again negative a square m square. Okay, so I am sending the term there, so it will be like you can say that c square is equal to a square plus m square. So after simplifying we can say that c square is equal to a square plus a square m square. So now I am taking a common, so it will be what, so value of c we will find, c is equal to plus or minus a times of 1 plus m square. Okay now, so now our line equation will be look like this. Y is equal to mx plus c. So this is mx and this is c. C is equal to plus and minus 1 plus m square. So this is my equation of the tangent. This is the general equation of the tangent. This always represent that it touches the circle. So now it always touches the circle. General tangent in slope form. So you can say that it is a general tangent. Always touches the circle. General tangent, and it is always touches the circle. Is it clear now? Okay. So now just you observe that this is the equation of the tangents. So now suppose this tangent actually passing through the point h comma k. If it is passing through the point h comma k, then what will happen? So y will become k and m, x become h, plus and minus a 1 plus m square. Okay now. So now if I am writing here k minus mh whole square, which is equal to a square 1 plus m square. So now it will be what? K square plus m square h square minus 2mhk, and here we have a square m square and 1 is the a square. So our target is I am going to make the quadratic in m square. So m square, if I am going to write, so there also m square is there. This term you have to take on the left hand side. It will be h square minus a square, and then you have m square and 2mhk. So here I have 2mhk, then plus here k square, and here you have minus a square, which is equal to 0. K square and minus a square, which is equal to 0. So which is the quadratic in m? So this will give the two values of m. One I am calling m1, other value is calling m2. So now sum of the roots we can find. Sum of the root SOR. Sum of the roots is m1 plus m2, which is equal to 2mhk divided by h square minus a square. Okay now. Product of the roots, POR. Product of the roots you have to prove m1 into m2, and here it will be k square minus a square by h square minus a square. Okay now. So now this is the point number what I am describing here, point number 9. So come to the point number 10. So suppose in point number 10, what we do, what will happen if the product of the slopes are, so product of the slopes. So first of all you try to understand what actually we want to doing here. So this is a circle, and for a given finite value of m, you have the two tangent. One tangent is look like there, that is your one tangent. For a given value of m, you having the two tangents. For a unique value of m, there are two tangents which are parallel to each other. Okay, so we are getting any one tangents we take, and if this tangent passing through the some point hk, then what will happen? Try to understand. Now no. So now we want to say that okay now. So now here we have these two tangents, they are passing through h comma k. Okay, here we notice that if you take any one of the equation of the tangents, and this equation is passing through the h comma k, so actually we have the two values of m. One is m1, so I am calling this one is m1 I am calling, and this value of m I am calling m2, this one I am calling, this value I am calling m2. So we have two values of m. The two tangents is actually passing through, or two tangents can be drawn any outsider point. So if a point lies outside of the circle, from that point we can always draw the two tangent to this circle. Now what will happen if these tangents, if the product of the tangents 4, which is equal to m1 into m2 is -1, that means I want to say that if this angle is 90 degree, so angle between the tangents is 90 degree. The product of the roots is, because m1 into m2 is the product of the slopes. Okay, now so if the product of the slope is -1, that means I am claiming that the two tangents are perpendicular. If this call this point P, this point is A, and this point I am calling B, so my target is, or I am claiming that PA perpendicular to PB. If it is happened, then what we can do, or what conclusion we can take? So our conclusion is, you have this result here, you have here these results here. M1 value is -1. So if it is happened, so now we can do that -1 is equal to k square minus a square divided by h square minus a square. So this will be h square minus a square, which is equal to k square minus a square with negative, and this will be the positive. So we can say that h square plus k square, which is equal to 2 times of a square. So now we are getting this equation, actually h square plus k square, which is equal to root 2a whole square. So now if you are this hk is what? This hk is the point of intersection of the two tangents. So this equation, the relation between the h and k represent the locus. So for locus we can replace h by x. So x square plus y square is equal to root 2a whole square. So this is actually the equation of the circle. This is the equation of the circle whose center is 0 0 and the radius is the root 2 times of the previous radius. So you can say that this is actually known as the director circle. This circle is actually has the name of this circle is director circle. So if I going to define this director circle, what will be the definition of the director circle? So it is the locus of the mutually perpendicular tangents. Locus of the mutually perpendicular tangents. So two mutually perpendicular tangent intersect at a point. The locus of that points are called the director circle. So director circle definition is clear. If two tangents drawn from any outside points are perpendicular, then the locus of this point through which we draw the tangents is known as the director circle. Locus of the mutually perpendicular tangents. Perpendicular tangents. Locus of the mutually perpendicular tangents. Okay, now? So we have the tangents and they are perpendicular to each other. So in that situation, the locus of the point of intersection of two mutually perpendicular tangents drawn to a given curve or the given circle is called the director. Locus of the point of intersection. This word we have to add, है ना? So it is the locus of the point of intersection of two mutually perpendicular tangents. Mutually perpendicular tangents drawn from a point which is outside of the circle. Okay, I think you understand from the figure also. No need to write everything, which are very important. Then in that situation we will write. Okay, now? So not only this way, without independent of the product of the roots, without independent of 4, you can also derive that the director circles equations, and in the next class we will in the next few points we will show you that without any help of 4 how can we find the equation of the director circle. So equation of the director circle, you notice that its radius is root 2 times of the previous circle, just greater than this one. So now the locus will be what, you know that if you are just draw the circle, now your circle will just passing through like that, this one. Okay, take more bigger one, like I'm showing you in the figure the director circle. It is actually a concentric circle, both having the same radius, both having the same, it is called center. Okay, so they having the same center, concentric circle and the original circle, they having the same center. Okay, so now they having the same center. Wait, yes, so they having the same center. Okay, now we are going to what happened to this my circle, why not this circle moving, left me. So this one, you understand that these things will happen. Okay. No, not like that, not like that. Okay, not like that. Now how can I show you that this circle I have to move there, but I cannot move it. Okay, whatever, try another one. So this is the concentric circle. Now this one may be this bigger one passing through the point, and I hope you understand this one. Now you observe that the second time I draw the yellow circle, that circle also passing through the point P. This smaller one is not required. Can we move it somewhere else? Okay, so now this one I don't want. Now I'm trying to rub it. Oh, by mistake it is happened. Okay, so this one I don't want. Yes, absolutely, I got the figure. Okay. So now this yellow circle now, which is the locus of this moving point P. This moving point P has the locus, and this locus is the bigger circle. This is the director circle actually. This is the director circle, and you know that this radius of this circle, if it is center of the circle, the previous radius whatever it is a, then it is just root over of 2 times a. It is slightly greater. So I hope all of you understand the concept of the director circle also. So now what I just discussed now, in short I am showing you that after the, now here I am describing diametrical form of a circle. Point number 5, how to find the equation intercept made by the circle on the x-axis and y-axis. What is their length? For the x-axis it is 2 times of root over g square minus root over of g square minus c, and for the y-axis it is 2 times of root over f square minus. Okay, yes, for the x-axis it is 2 times of root over g square minus c, and for the y-axis it is 2 times of root over of f square minus y. Okay, now position of a point with respect to the circle we are discussing here. S1 greater than 0, equal to 0, less than 0. Then we have the parametric form. If the center is given, the center plus radius into cos theta, center plus center coordinates of the center, then radius plus into y into radius. X is equal to x1 plus r cos theta. That means x coordinate is equal to center plus radius time of cos theta, and y coordinate is equal to y1. That means a new center plus center of the circle plus r times of sine theta, radius into sine theta. Okay now, and if the center, if the equation of the circle is x square plus y square equal to r square, then the parametric form is very easy. Equation of the tangent in different form. So there are three form for the tangent. One is the Cartesian form, then is the parametric form where we use the sine theta cos theta, and we put the restriction on the theta. Here we put the restriction on theta, 0 to 2 pi, pi is excluded, and one is the parametric form done, Cartesian form done, then the slope form. Slope form is more important, where we show that y is equal to mx plus c. If the tangent to the circle, then what will happen actually? What will happen actually? The c will be a times of root over m square, and there will be the plus minus sign. So c is equal to plus minus a root over 1 plus m square. Okay now. So next we are going to discuss more theory. So up to the point number 10 we have discussed. So now coming to the next point, point number 11. So now we are going to discuss the point number 11 here. In the point number 11, we are going to discuss the equation of the chord with a given middle point. That means the midpoint of the chord is given, then we have to calculate what will be the equation of the chord. So now for this purpose, first of all we draw one circle. So suppose this is my circle, like this one, and I am taking one chord like this. This is the chord. Okay, now whose midpoint is given to us, whose midpoint is known to us. Okay, now whose midpoint is known to us. So suppose the midpoint of this chord, the name of the chord is AB, and its midpoint is given as h comma k. Now we are going to calculate the equation of this line. So when you are going to calculate the equation of a line and the line is passing through the point h comma k, if you know anyhow the slope of the line, then the line can be measured, or they can be find out uniquely. So here the center of the circle I consider as 0 comma 0. So now my circle is like in this way, x square plus y square, x square plus y square, and the radius I consider is as a square. Okay now. So now what I do, from the point O I join this middle point M. So as a result I am able to find out the slope of this line OM. So slope of this line OM is nothing but k by h. So what about the slope of this line AB? The slope of the line AB is minus h by k. So since we know the slope of the line number 1, and we also know that the line passing through the point h comma k. So now question arises, can we find out the equation of the line uniquely? Answer is yes. So it will be y minus y1. So my point is h and k. So y minus k is equal to slope of the line minus h by k, and then x minus h. Okay now. So now multiply both side by k. So it will be k into y minus k, and here we have minus h into x minus h. So now k into y, it is ky, minus k into k, k is square, and here we have minus hx, then plus h square. So this can be written in this way, ky, and then you have hx, and which is equal to k square and then h square. So now what we observe, that h square, k square plus h square is there. So if I add both side, minus a square, so what will happen? H square plus k square and then minus a square. Okay now. So this value you notice that this is the equation of the tangent. Okay now, this is the equation of the tangent. If I write in this way, s is equal to x square plus y square minus a square, and if we calculate here the t at the point h comma k, so it will be what? T at the point h comma k, x into h plus k into y minus a square, and this will be the 0. So similar way here you get this quantity, which is nothing but the tangent at the point h and k of this circle. So this is the equation of the tangent. On the right hand side it is same as when you put hk in the equation s, so you are getting that point. So it is nothing but you can say that s1. So we take therefore t is equal to s1 is the equation of the chord when we know the midpoint of the chord. So here S1 is nothing but h square plus k square minus a square. So in the equation of the circle, when I replace x and y by hk, so this is I written by the symbol S1. So now this is the equation of the circle when the midpoint of the chord is given. Equation of the, sorry, it is the equation of the chord. Okay, now it is the equation of the chord when the midpoint of the chord is given. So in this way we can calculate the equation of the chord. Now coming to the point number 12. In this case we are going to find the equation of the chord of contact. Equation of chord. Equation of chord of contact. Equation of chord of contact. That is COC, chord of contact. So what is the meaning of it? So first of all, take one circle. This is our circle, and through one outside points, we are drawing the tangent. We are going to draw the tangent to this circle. Okay, so from here okay, now what will happen? This is the tangent. No, the figure is not correct. Wait. Somehow we get this point. So one tangent we draw from the point, this point I call P, x1 y1, and this point I called that A point, which is x dash comma y dash. Is it okay? Now from this point P we are going to draw one more tangent I am going to draw. So this will be like that. So now we get the another tangent, and this tangent is drawn at the point through the point P x1 y1, and it touches the circle at the point B, which is x double dash comma y double dash. Is it clear? So when we joined this line, this line AB, which is the this line AB now is known as the line AB is known as the COC, chord of contact. So first of all, okay, this is known as chord of contact, COC. So is it clear? This is the points where the tangent touches the circle. So if we join these 2 points, we get the chord of the circle. This chord is known as the chord of contact. Now our target is we are going to calculate the equation of this COC. So first of all, I consider our circle S is which is same as x square plus y square, and the radius is a square. So can we find the equation of the tangent? Equation of the tangent at x dash y dash, at the point x dash y dash. So it will be what? X dash plus y dash minus a square, which is equal to 0. This equation I called 1. So this is the equation of the tangent at the point x dash y dash. Now this tangent is passing through the point x1 y1, so we can write as x1 x dash plus y1 y dash minus a square, which is equal to 0. This is our point 2, equation 2. Now I am going to calculate equation of the circle, equation of the tangent at the point x double dash y double dash. The equation of the tangent at x double dash comma y double dash. So this will be what? X into x double dash plus y into y double dash minus a square equal to 0. This equation I give the name 3. For this equation I call this equation is 3. Now this is passing through the point x1 y1, so it will be x1 x double dash y1 y double dash minus a square, which is equal to 0. So this is my equation 4. Now I am going to calculate the equation of the tangent at the point x1 y1. Now equation of the tangent at x1 y1. So at the point x1 y1, when we draw the equation of the tangent, when we find the equation of the tangent, it will be x1 plus y1 minus a square equal to 0. This equation I call 5. So now if this equation I passes through this equation, if you put in the place of x and y, if x comma y is replaced by x dash comma y dash, so what will happen? You notice that it will be x dash x1 plus y dash y1 minus a square, which is equal to 0. So this equation that we obtained 6, equation 6, so this equation 6 is same as, you notice that it is same as the equation 2. So this equation is same as equation 2. So now if you replace, if you make the line passing through the point x double dash y double dash, then what will happen? So you notice that it will be x double dash x1 plus y double dash y1 minus a square equal to 0. Now this equation 7 is same as, you can notice it is same as equation 4. So what I can say that, what we can say that equation of COC, now from this 6 and 7, okay, now 6, 7 and 5, so from 5, 6 and 7, so we can say that equation of COC is nothing but x1 plus y1 minus a square equal to 0. So which is same as t is equal to 0, tangent at the point x1 y1, which is same as this equal to 0. Is it okay? Now any 1 degree equation in the variable x and y always represent a straight line. So if your straight line passing through the point x dash y dash and x double dash y double dash, so it indicates that the through 2 points we can draw only one straight line. So this idea is clear. What I say, I'm saying that the 1 degree equation with the variable x and y is always represents a straight line, and our straight line passing through the point x dash y dash and x double dash y double dash. So these 2 points, if a line passing through the 2 points, then the line is fixed. And you can uniquely determine that line. So here you notice that in the graph, this is the line which is passing through the 2 point x dash y dash and x double dash y double dash. So by the tangents, by the equation of the tangent at the point x1 y1, whatever we are getting, which is nothing but the COC, okay now. So which is nothing but the equation of the chord of contact. So this one is the equation of the chord of contact, okay now. So remember this one, very important formula. So now we notice that there are three types of chord in a circle. One chord, when the two ends are given, you can easily calculate. When the midpoint of the chord is given, then S is equal to T1. When the two tangents are drawn from a single point, outside point, when two tangents are drawn, then when we join the foot of the foot, then we get a chord. So in this case, it is known as the chord of contact. So how do you calculate the chord of contact? By considering the equation of the tangent at that point x1 y1. What is the result we are getting? That is the equation of COC. So there are three types of chord in the circle. Number one, normal chord. When the 2 points are given, you can calculate. Number two, midpoints are given. How to calculate? S is equal to T1, and third is T is equal to 0. That is the equation of the tangent at the outside point x1 y1 is same as the equation of chord of contact passing through the point x dash y dash and x double dash y double dash. So now we have discussed the point number 11 and point number 12. Both we have discussed. Now coming to the next point, point number 13. Now in the point number 13, we are going to discuss pair of tangents. So what are pair of tangents? Pair of tangents. So here we are going to find out the combined equation of the pair of tangents drawn from an external point P to a given circle. So now combined equation of pair of tangents. Combined equation of pair of tangents drawn from an external point. Drawn from an external point P. Drawn from an external point P to a given circle. Circle is S1 is equal to T square. So when we are going to calculate the pair of equation, and these two equations are drawn from the any external point, then the formula will be S1 equal to T square, where we consider S is the standard equation, that is x square plus y square minus a square, and S1 I am taking, and S1 we are taking x1 square plus y1 square minus a square, and T is equal to nothing but the equation of the tangent at the point x1 y1. The equation of the tangent we are taking at the point x1 y1. So T is equal to x1 plus y1 minus a square, x1 plus y1 minus a square. This will be the equation of the tangents. Okay, now here we have this one. So now how can we calculate So here pair of tangents means we are going to calculate the combined equation of the pair of tangents drawn from an external point to a given circle, and that will be the S1 equal to T square, where S is equal to x square plus y square minus a square, and S1 is equal to this coordinate P points coordinate is x1 y1 drawn from an external point P. This point P has the coordinate x1 y1. So now S1 is equal to x1 square plus y1 square minus a square, and T is equal to x1 plus y1 square y1 minus a square. Okay, now so now we are going to prove these results. How can we prove this result? S1 equal to T square. S1 equal to T square. So first of all we draw the one circle. So for this purpose we draw one circle. Okay, now we draw the two tangents from the external points, so there are tangent 1 okay. Now next is another tangent is there, this one. So now another tangent is look like this. So now we have two tangents, and just we in the previous sections we had told that when you join the points of tangency where the tangent touches the circle, when you join them you will get a chord. This chord is known as chord of contact. This chord is known as actually chord of contact. So this is our chord of contact. So just we see that chord of contact also has the very simple equation, and this equation is nothing but this equation. Okay, now so this is the chord of contact, and the name of the chord of contact I have given here, AB. This is our P point through which two tangents are drawn, x1 and y1. The equation of AB we can write in this way. Equation of AB will be x1 plus y1. Okay, now x1 plus y1 minus a square equal to 0. That means t is equal to 0 is the equation of the chord of contact AB. Is it clear? Now next I am going to do just add through the midpoint and the vertex I am going to add, because it is an isosceles triangle. So if you join this perpendicular midpoint of this chord so this point I called M, which is the midpoint of this chord, and if I joined with the P point, what I notice that these will be, suppose these and these are isosceles triangle, so these two are equal. This perpendicular if I called P1, this perpendicular I called P1. Now another arbitrary point I am taking here, P, whose coordinate is h comma k, and through here I am drawing one more perpendicular. So this perpendicular I give the name N, and this is my P2 perpendicular. Okay, now so here you notice that the triangle ANP, this triangle is similar to the triangle AMP, because one angle you are noticing that 90 degree one thing, and the lines are parallel, so these angles should be equal. This one and this one must be equal. So by angle similarity, you can say. So if the two triangle are similar, then what we can say, ratio of their corresponding sides are equal, or the sides are proportional. The ratio of their corresponding sides, I am taking this perpendicular is P2, so this perpendicular is P1, which is equal to, now this hypotenuse length is AP, and its hypotenuse length is it is also I am calling P. Achha, give the name, it is R. So if it is AR, so now it will be AP. Okay, now so now this P1 is the perpendicular distance from the R point, and this from the chord of contact. So now what we are doing, we know how to find out the perpendicular distance. So for P2 the value equation we already know. This is the equation of the chord of contact AB. So for P2 we have to replace x and y by h and k. X and y we have to replace by h and k. So it will be hx1 plus ky y1 minus a square, then divided by a root over of we have here coefficient, wait, yes, we have the coefficient of x and y as x1 y1. So here we have root over we have x1 square plus y1 square. For p1 we have this value, um, uh, point is x1 y1, so we have to substitute x1 into x1 square, y1 into y1 square minus a square, then whole divided by, you have to actually take the modulus also. So modulus, here we have also x1 square and then y1 square. AR, you know that AR is the length of the tangents. AR is the length of the tangents. It is nothing but root over of h1. So here the coordinate is h comma k. We have to put in the circle. So circle equation x square, that means h square plus k square, and then we have minus a square. Now we are going to calculate AP, which is equal to root over of s1, but here the point is x1 y1, so it will be x1 square plus y1 square minus a square. So all these four value I am going to put here, but before that what I am doing, taking the square so that root sign will be cancelled. So here p2 value, first we have to put p2 value, which is h x1 plus k y1 minus a square whole square divided by x1 square and y1 square. This term actually cancel out from the denominator term, so no need to write. Now coming to the p1 value, which is x1 square plus we have y1 square minus a square. Now here we have AR value square is h square, then we have k square minus a square. Here we have x1 square plus y1 square minus a square. So when you do the square, here will be one square signs. So now from the denominator one term we can cancel out, so here only one. So what I have actually h x1 plus k y1 minus a square whole square, which is equal to h square plus k square minus a square, and then we have here x1 square plus y1 square minus a square. Okay, now so it is nothing but the equation of the tangent. So this is we are calling t square, and this is s into s1. So this is nothing but s into s1. So here you can assume that, or you can replace this before making t square as s1, you should replace h and k by x comma y, so that you can easily generalize the relation. So dear students, when we are going to find out the pair of equations from the some external point x1 y1, so formula will be s1 equal to t square. So pair of tangents, combined equation of pair of tangents drawn from an external point P whose coordinate is x1 y1 to a given circle x square plus y square equal to a square is s1 equal to t square, where s is equal to x square plus y square minus a square, where s1 is equal to x1 square plus y1 square minus a square, and t is equal to x1 plus y1 minus a square, the whole square. This is the very important result, that s1 equal to t square. So these results we used in problem solving. So now in point number 13 we are discussing the pair of tangents. Now coming to the next point, and we go for the another concept. Here we are going to in point number 14 we actually describing the family of circles. So this may happen, we can categorize into the four types. So type number 1, type 1. Now the equation of the family of the circle passing through the point of intersection of two circles is s plus lambda times of s2 is equal to 0, where s is s1 plus lambda times of s2 equal to 0, where s1 is the equation of the circle x square plus y square plus 2g1x plus 2f1y plus c1 is equal to 0. s2 is the equation of the circle, which is equal to x square plus y square plus 2g2x plus 2f2y and plus c2 is equal to 0. So now these are the equation of the circle. Here lambda is the parameter. lambda is equal to parameter, it can be any value but except -1. So what type of equation we are actually, what type of circle we are actually obtaining? This is suppose S1 circle and this one is my S2 circle. So they will intersect at the point A and B, suppose here. So we can describe infinite number of circle, passing through the point A and B. We can describe infinite number of circle passing through the point A and B. Like this we can describe, okay now. So many circles are there. We can describe which passes through the point A and B, because we are just joining these 2 points A and B. We will join, and we are taking their perpendicular bisector. So in the bisector, if you take any points here, then you can easily construct one circle which passing through. If it is the center and OA is the radius, then you are getting this one. This one is the circle. This one is your circle, like this, है ना? Like this you are getting the circle. So infinite number of circle we are getting in this way. But why we put the restriction lambda cannot be equal to -1? Because we are taking the two circle in the general form, and if you are doing S1 minus S2, so it will be 0, and here you are getting the linear term only, linear terms in the variable x and y. So linear terms only you are obtaining, and which represent a straight line. So that's why we cannot take lambda is equal to -1. One more thing is here. This expression represents all the family of the circle passing through the point S1, S2, except S2 circle, except S2, because we cannot find S2 from here except S2. From this relation, whatever the value of lambda you are assigning, you never get S2 equal to 0 from here. Okay na? So but we still using there this formula. Now all the members you are getting which passing through A and B except S2. So is there any way so that we can also find the S2? So one way is there. If you write here lambda S1 and plus mu S2 equal to 0. So if lambda is 0, then you get S2 is equal to 0. Okay now. So in this way, more general way, if you express the equation in this format, then the member S2 can also be included in the set. So first type 1 is the family of the circle we are going to calculate, which passing through the point of intersection of two circles. Now our next target is type 1, where we will describe the family of the circles passing through the point of intersection of one straight line and one circle is there. Type 2 it is. Type 2. So one circle is there and one straight line is there. Okay na? So we consider one circle and one straight line. One straight line we are taking like this one. So in this case we have infinite number of family member which passing through the point of intersection of these two A and B. So now type 2, the equation of the family of the circles, which passing through the point of intersection of the circle S and the straight line L is equal to 0 is S plus lambda times of L equal to 0, where S is the equation of the circle and L is the equation of the line. So we consider in this way S is equal to, suppose the standard form you are taking, no problem, x square plus y square plus 2gx plus 2fy plus c is equal to 0, and L you can take as ax plus by plus c is equal to 0. Okay, but here both are c, so I am just change the variable. I am going to change the variable. So here instead of ax plus by plus c, I am taking lx plus my plus n. So lx plus my plus n is equal to 0. So this is my equation of the line and this is the equation of the circle. So if you have these two, they will intersect at certain points A and B. So we can find the infinite family of circles which passing through A and B, and their equation will be represented by S plus lambda L equal to 0. And converse is also true. If any equation have S plus lambda L equal to 0, then you can say that they are passing through the intersection of the point of intersection of the circle is equal to 0 and L is equal to 0. Why? Because if you consider any point x1 y1 of the point A, and if you put here, so you know that this point is present on the circle, so it satisfies the equation of the circle. At the same time, this point is on the line, so it also satisfies the equation of the line. So line also becomes 0. S1 is also 0. Their combination should be 0. So any point satisfies this equation. So if any point satisfies this equation, that means it is on the intersection of the circle and the line. Okay, now I think it is clear to all. Coming through the type 3. So in type 3 I am going to describe, in type 3, find the equation of the family of the circles which passing through the point of intersection, which passing through the 2 point x1 y1 and x2 y2. Listen carefully. Find the equation of the family of the circle which passing through the point x1 y1 and x2 y2. So what we are doing here, we consider a circle like diametrical form x minus x1 into x minus x2, plus we are taking y minus y1, and then we are taking y minus y2. So this is what, this is the actually the equation of the circle in the diametrical form. So it is circle we have now, plus lambda times of we get L. Lambda times of we get L. L is the equation of the line which we can form with the help of these 2 points. So it is nothing but x, y and 1. Here x1, y1 and 1, and here you have x2, y2 and 1, which is equal to 0. So here also lambda is the parameter. So now family of the equation of the circle passing through, family of the equation of the circle passing through the 2 points x1 y1 and x2 y2, we can write in this way. So among all the family of the circles, you can do one thing, we can find the fixed circles also. So fixed circle can be drawn which has the end of the diameter x1 y1 and x2 y2. So fixed circle of this family is the circle described on AB as the diameter. So from this equation you can also find one fixed circle is there. Fixed circle you can also find. So which one is the fixed circle? A circle whose diameter is AB, whose diameter is AB, that circle will be the fixed circle. So here we consider this one is A and this one is the B. So AB, we obtained a fixed circle. AB is the fixed circle here. Okay, now AB is the fixed circle. Not the fixed circle, a circle having the diameter AB is the fixed circle. So this is the type 3 where we are discussing a circle passing through the 2 point x1 y1 and x2 y2. So suppose these are the point A whose coordinate is x1 y1, and here point B is there whose coordinate is x2 y2. Okay, now next is type 4. Here we are going to discuss the family of the circle, equation of the family of the circle passing, equation of the family of the circle touching a straight line at its fixed point x1 y1. So one line is there, L is equal to 0, and one point on the line is x1 comma y1. So all the circle touching this line, all the circle, suppose this is a circle. Now you can take another circle also, this one, this one, like that. Okay, now so from here you can get this. Now another circle is there which touching at the same point. Now you can make one more circle, you can also make one more circle here. So now this will be the circle. So now you can take this circle touching here. Okay, now so so many circles are there, all touches the point x1 y1, all touches at the point x1 y1 and of this line which is the fixed point for the line. Okay, now so here we call this point, this one is x1 and y1 point, and this is the equation of the line L is equal to 0. So how can we find the family, equation of the family of the circle? equation of the family of the circles where each member touches the line at its fixed point x1 y1. So first of all we try to make the point circle. So now x minus x1 whole square plus y minus y1 whole square plus lambda times of L is equal to 0. So we are taking here x minus x1 whole square, that is our point circle, y minus y1 whole square plus lambda times of L is equal to 0. Okay now. So here this is the point circle whose radius is actually 0. This is we are called point circle. So point circle, and here L is the straight line. So in this way we can find all the members of the family for the different value of lambda. Each member you can find. If you take lambda is equal to half, you get suppose green circle, lambda is equal to 1, you are getting the white circle like this. So first of all it represents the circle what is the conditions, because here the x and y, the coefficient of x square and the coefficient of y square is same, and no term of xy present here, so it must represents a circle. Number one. Number two, now how can we prove that the circle is passing through the touching the straight line at the fixed point, at its fixed point x1 y1. So if you choose the point x1 y1 and if you put in the straight line L, it will be satisfied. And again if you put here x1 and here y1, so this quantity becomes 0. So x1 y1 satisfying these conditions, so every member of the circle must touches this line at the point x1 y1. So in this point we describing the family of the circles. So there are four conditions in the point number 14. So for the family of the circles there are four types of the family of the circle exist. Number one, the equation of the family of the circle passing through the point of intersection of the two circles s1 and s2, that is lambda s1 plus lambda s2 equal to 0. Now second thing is the one line and the one straight line and the circle, if they intersect, then the equation of the family of the circle passing through the point of intersection of the line and the circle. Now the type 3 is what? The family of the equation of the circle passing through the point x1 y1 x2 y2. Okay, now third is the equation of the family of the circles which touches the straight line at its fixed point x1 y1. So there are these four types of family of circles we are able to find and we discuss here. Now coming to the next point, that is point number 15. So in point 15 we are going to discuss about the tangents. So in the point number 15 we are going to discuss about the tangents. So how many types of tangents we generally have? So we have two types of tangent. One is the direct common tangents, and another, it is in short you can write as DCT, direct common tangent, and second type is inverse common tangents, or you can say that transverse common tangent. Inverse or transverse both are correct, so I am taking the name transverse, TCT, transverse common tangent, transverse common tangents, you can say that CTC, transverse common tangent. So one is the direct common tangents, other is the transverse common tangents. Okay now. So now we have some result regarding this DCT and CTC. So DCT, direct common tangents, so we have two circles. So now I am going to draw the circles like I have this circle and another, I have this one, this circle I have. Okay now. So you can put the photo above like this one. Yes. So now we can draw the direct common tangents. So first of all you understand what is the meaning of direct common tangent. Direct common tangent means when the centers of the circles lie on the same side of the tangent line. So here if I draw the tangents like this one, if I am going to draw the suppose tangents like this, so what you notice that both the center of this circle both the center of this circle, you notice that both the center, so both the center of this circle lie on the same side of this circle, yes or no? So here you are getting one direct common tangents, and now another direct common tangents we can draw like this. This is also the another direct common tangents. So in both the cases, your center of the circle, you notice that lie on the same side, lies on the one side. So with respect to this one, if it is A, it is B. So what I observe that the center C1 and C2 lies just below the AB line, and if you take CD, this point is C, this point is D. So now you notice that both the tangents, both the centers lies on the one side of the tangent line above the line CD. Now what will happen if you increase this, line, then what will happen? If you increase this tangent, they will intersect at some point, like here. If you increase that value like this, like this, if you increase, okay, like this, you can notice that. And if you increase the red line also, you notice that they will intersect at some points. Yeah, they will intersect like this, okay, like this they will intersect. Okay. So no need to go that side, no need to require it. So actually they will intersect at some points, okay. Now, so now here I am taking like this one, okay. And here also you notice that they will intersect at here, like that. Actually diagram is not correct. What I do, first of all I rub this one, to rub this part also. So now I want to show you that if they intersect at some point, then what will happen, what actually happened. So with the hand I am going to draw so that it will be look like this, and it will be look like this. If they intersect at some point here, like P point, so now you notice that P is the point of intersection of these tangents, and if I joined the center of the circles with the points P, so now here we can prove that they divide in the certain ratio. That means I want to prove PC1 by PC2. This value will be something very exciting, okay. So now if you join this one, so it is 90 degree. If you join this one also, it is also 90 degree. So both the triangles, this triangle PC2B and PC1A, are the similar triangle. So since they are similar, which is same as their radius R1 by R2. So now I want to show that if the in case of the for DCT, the point of intersection of the tangents of the two circles, it divides the line segment joining the center of the circles in the ratio of their radii externally. So this division is external division. This division is external division. This division is external division. Okay now. So now next is for CTC. CTC is what? In case of CTC, TCT, transverse common tangent, we notice that, or we will see that the center of the circle lie on the opposite sides of the tangent line. So we draw two circle first. So this is my circle 1. Now next circle is like this one, is the next circle, okay. It should be smaller, okay, no issue. So now direct common tangent is the line which touches both the circle, and here you notice that the center of the circle lies on the opposite direction. Center of the circle lies on the opposite sides of the circle. Center of the circle lies on the opposite sides. Okay, now what will happen, I don't know. Okay. Wait, these I can do like that. Yes, no, not like that. If I take the smaller one, okay, here also if I paint like that, now it will work. No, some rotation. Yes, yes, it is working, dear. Okay. So now what we notice that in case of a transverse common tangent, the center lies on the opposite side of the tangent line. So this is our one tangent. Now another tangent we can draw like this we can draw now. Yes, so this will be the another tangent. So here we notice that the transverse common tangent, there are two transverse common tangent and they are intersecting at this point. So if they call this point is P, now if you join C with P and P with C2, so what you observe that PC1 divided by PC2, which is nothing but the R1 is to R2, but here the division is the internal division. Here the division is the internal divisions. So now we can say that the point of intersection of the tangents for TCT, for the transverse common tangents, divides the line segment joining the center of the circle in the ratio which are R1 is to R2, and it is the internal divisions. So here you notice that we are getting, how can we prove this? So first of all, this you can join and give the name M. This is 90 degree, this is the radius R1. Similarly, you can join these two also, the radius is R2 and this angle is 90 degree, and you can take the vertically opposite angle also. So since the two triangles are congruent, so PC2 by PC1 you can take as R1 is to R2. So we can say that for TCT, for the transverse common tangent, both the center of the circle lie on the opposite side of the tangent lines, and the point of intersection of the tangent divide the line segment joining the centers of the circle in the ratio of their radii internally. Okay, now next is we want to know for the different position of the circles how many tangents are there. So our next is point number 16. Point number 16. Number of tangents. Give the heading number of tangents. Number of tangents. So we consider two circle and we are going to calculate how many tangents are there. So first of all, take the circle like this. This one is the one circle. Another circle we can take this one. This one is the another circle. So you notice that how many tangents we can draw. So first of all you notice that there is one tangent, that is the direct common tangent here. Now another is again one direct common tangent, you can draw one direct common tangent, this one. So two direct common tangent you can draw. Now coming to the transverse common tangent. So from here you can also draw the transverse common tangent. One transverse common tangent is like this, and another transverse common tangent you can draw like this. Okay na, you can draw like this, another transverse common tangent. Okay na, you just try to understand what actually happened here. Okay na, so now here also. Okay, is it clear to all? So therefore what is the condition that the circle are not intersecting? That means case 1 we have to take when the circles are separated, when the circles are not intersecting. So circles are separated. So this is my word, but in mathematically if you want to show circle are separated, so you have to prove, you have to make the condition like that, if it is C1, if it is C2, so joining their center the length is C1 C2 and it must greater than the sum of the radius R1 plus R2. So this is the condition when the circles are separated. So how many tangents you have? So how many tangents, common tangents, how many cities? 4 cities are there, and this can be divided into two parts. Number 1, 2 DCT you have direct common tangent, and 2 you have TCT, transverse common tangents. So now coming to the second case, suppose both the circle are touches each other, then what will happen? So this is the first circle, and now we are taking another circle also, and they are touching each other but externally. So they are touching each other but externally, this one. Now take the circle here touching them. Okay, so now you also notice that here what will happen, the first is you have one direct common tangent here. Now second, again you have one more direct common tangents. Third one, you have the TCT, transverse common tangents. You have transverse common tangents you have, if you are drawing this one, transverse common tangents. So here first of all what will be the restrictions, and we say that the circles are touching each other externally. So touches each other externally. So this is the criteria, externally they are touching each other. Now what is the condition for external touching? Condition is when we join their center, this one and this one, so this is sum of the radius. So condition is C1 C2, this distance must be is equal to R1 R2. Now third one, we can also say that how many tangents are there? So 3 common tangents are there, not CM, CT, common tangents. So 3 common tangents are there, out of which 2 are the DCT, and we can say that one is TCT. Third condition may happen that 2 circles are intersecting. Then what will happen? So now we are taking the 2 circles which are intersecting circles. Not like that, you are take here. So one circle is like that, and another circle is like this one, and they are intersecting. Okay, now they are intersecting. So take here and make them intersect. So if 2 circles are intersecting, then we notice that number 1, first of all, one DCT we are obtaining here. This one is the one DCT. Another DCT we are obtaining in the lower part, this one. So 2 DCT we have, and no TCT. TCT is not present there. So now we can write here the intersecting each other. So if 2 circle intersects, intersecting circle, so for what is the condition that they will intersect? So first of all, if you join their centers, that is C1 and C2, so C1 C2 is lesser than R1 plus R2. Okay na, but it should greater than R1 minus R2 whole mod. So this will happen. So in this case we are getting the common tangents, total 2 common tangents we have. Total how many common tangents we have? 2 common tangent, 2 CTC we have, and 0 TCT, DCT, direct common tangent. So now here we are going to write this one. So now tangents, total number of two common tangents are there. So number 1, 2 dct, 1 tct, transverse common tangent, 0 transverse common tangents. Coming to the fourth case, when one circle touching the other circle but internally, then what will happen? So this is our circle. Another circle is there like this one. Now this circle touches the bigger one like this. So what will be the condition? So here we say that touching each other internally, touching internally. So what is the condition for this? So this is their centers. One is C1, other is C2. So this distance C1 and C2 same as modulus of R1 minus R2. Internally they are touching. This is the conditions. So how many tangents we have? Only one. All of you know that there exists only one common tangents, and both the centers lie on the same side of these tangents. So these are the direct common tangents only. So number of tangents, we can say that common tangents. How many common tangents we have? Only one. And this is 1 dct, direct common tangent, and 0 tct, transverse common tangent is 0. Case fifth may happen that one circle is strictly lies inside the other circle. So now here we have the condition. This is our, suppose bigger circle is there and one circle is strictly lies inside the circle. One circle is strictly lies inside the circle. So one circle is like that. So in what cases it will happen? One circle is lies inside the another circle. So here also you notice that the distance of their center, if you consider, so suppose this is the center. So now here C1 and C2. So this centers C1 and C2, this value is lesser than mod of R1 minus R2. If it is happened, then you can say that there is no common tangent, no common tangents, no CT. There is no common tangents. Okay now. So now I'm going for summarize this point. Point number 16. Here we are going to calculate the number of tangents. If two circles are not intersecting, they are separated. That means their joining centers length must be greater than the sum of their radius. If it is happened, then there are 4 tangents. 2 is the direct common tangent and 2 is the transverse common tangent. If two circles are touching each other externally, then we see that there are 3 tangents are there, and the condition for the external touching is C1, C2. This length should be equal to the sum of the radius. So 2 direct common tangent and 1 transverse common tangent. If one circle intersect the another circle, then there are only 2 direct common tangents, and the condition is C1 C2 less than equal to sum of the radius but greater than is equal to sum of the radius and greater than R1 minus R2. When one circle touches the another circle internally, then in that cases R1 minus R2 is same as the C1 C2, and only one direct common tangent exists. If one circle lies inside the another circle, strictly lies inside the another circle, then there is no common tangents. So in the point number 16 we discuss all these things. Now coming to the point number 17, where we are going to calculate the length of the direct common tangent and length of the transverse common tangents. Okay now, so length of the tangents we are going to calculate. Length of the tangents. Length of the tangents. So for first is DCT, direct common tangents. How can we calculate their length? So first of all I am taking this circle, one circle, another circle is like this one. Okay now. So now our tangent is like that. 2 direct common tangents are there. One is like this one and other is like this one. Other is like this one. So we have 2 direct common tangents, these and these we have. Okay now, our target is to calculate the length of this. Okay now, so how can we calculate? So first of all we join their centers. This is the center of the circle. Okay now, give the name of the centers. The first circle having the center C1, second circle having the center C2, and here is the point A, it is the point B, this is the point C, and this is the point D. So now I can write as A, this is my B, this point is C, this point is D. If I joined with the center, this will be nothing but 90 degree. This will be nothing but 90 degree. And if I join this one, this is also 90 degree. Is it clear? This is our R2 radius and this is my R1 radius. So if I cut R2 radius from R1 up to this, and if I joined, so what I notice that if it is R2, opposite direction is also length is R2. So this length we can say that R1 minus R2. Now AB, this is if I say D, so this length is also D. So now we are going to calculate, this is C1 C2, this length is C1 C2. Now here one here one 90 degree is formed, one right angle triangle we have. Okay, now what we are going to calculate, length of the direct common tangent. That means we have to calculate the D1 D2. So now here we apply the Pythagoras theorem and we write this D square and this one R1 minus R2 whole square, which is nothing but distance between their center whole square. So from here we can write D square is nothing but C1 C2 whole square minus R1 minus R2 whole square. So this is the formula by which we can easily find the length of the direct common tangents. Now what will happen to the transverse common tangent, TCT? So for TCT we are taking the two circles again. Two circles we are going to take this one and one more circle. This one. Okay, now so now here we have this value. First of all, we want to draw the transverse common tangent, these and this one. If they touches each other, number one. Number two, we have this value also. Okay, now joining the centers, if we joint, it will be look like this. Okay, now give the name here C1 and this value is I am giving the name C2. So we are going to calculate the length of the transverse common tangents. So for this purpose we have to make one rectangle. Okay, now so this and this value we joined, this and this value we are going to join, and here we join this and this one, so that we get one rectangle. So now from here this is actually not required, this blue line, another tangents, so it makes the figure complicated. Now erase. Sorry, what happened? This one I don't want. Okay, so now what I am doing, I am drawing a line which is parallel to this red line, and next I am drawing the line which is parallel to this CM. Okay, now which is parallel to the CM and through the point C2. Okay, like this. So this is our R1 and this value is R2, this value is R2. Okay, and this value is lower part is R1. So you notice that the full part from here to here, if you give some name here N, so NC2 is nothing but R1 plus R2. R1 plus R2 is the NC2. Okay, now this one. Center we don't know anything about the center, and this is C1N C1n is same as m, this point P. So if you call this is D, this will be the D. So D I have, R1 R2 I have. So now here I am going to apply the Pythagoras theorem. This angle will be the 90 degree because here 90 degree is formed. So now we have C1 C2 square is equal to perpendicular and base square, perpendicular square and base square. It is a right angle triangle, right angle forming here. So from here we can find D square, which is equal to C1 C2. Acha, here one thing I have done wrong. When I am taking the square root, we should move the root sign. So here you have this value is like C1 C2 whole square minus R1 plus R2 whole square. So here also we have to remove this sign square. So this is the direct common tangents and this is TCT length, TCT transverse common tangent length. So you notice that DCT and TCT out of 2, this value DCT is greater because here you are subtracting more value. So if you subtracting more value, this value will become the less. So DCT, length of DCT is generally greater than, for the same set of circle, is generally greater than TCT, transverse common tangents. Okay now, so here I am describing the length of the tangents in the point number 17. So there are two type of tangent. One is the DCT, direct common tangent. One is the TCT, transverse common tangent. So in case of a direct common tangent, what we have to do, you have to just take the radius R2 and cut from the C1A from the point A. So you will get the rectangle. After the rectangle, below portion, this one is nothing but R1 minus R2. So this is R1 minus R2, you know, and this length we consider as D. Now this is we are going to calculate. Okay, so now D we are going to actually calculate. C1 C2 is given. So if we apply the Pythagoras theorem here, so we can write D square, perpendicular square plus base square equal to hypotenuse square. So hypotenuse square minus R1 minus R2 whole square is the value of the length of the tangents, direct common tangents length. So here C1 C2 very simply we can calculate because the coordinate of the centers are given. So we can easily calculate C1 C2 square, radius are known. So we take their difference and do the square and then subtract it. For the direct common tangents, what we are doing, we are actually making one rectangle with one side is MP and other side is C1M. This is C1. So two sides are given which are perpendicular. Two adjacent sides are given with 90 degree angle between them. One is the C1M, another is the MP. So we complete the rectangle. After completion of the rectangle, this length we are going to calculate. So this part you know that R1 and this part is R2. The total part is R1 plus R2. So in the base of the triangle you are getting R1 plus R2 and this length actually this one we want to calculate. D I denoted by D. So this is and this hypotenuse is nothing but the distance between the center. So distance between the center whole square minus R1 plus R2 whole square is equal to the D square. So from there we can calculate D is equal to this one. So if you notice that you are going to subtract more value from the C1 C2 square, so that's why this value become the lesser compared to this D. So we say that DCT length for the same set of circle is more than the TCT length, transverse common tangents length. Now we are discussing the point number 18. Okay now, so now we go for the point number 18 and we discuss something interesting here. Now in the point number 18 we are going to describe radical axis of two circles. Now here I am going to describe radical axis of two circle. Now what is actually it? The radical axis of two circle. The radical axis of two circle is the locus of the point with respect to the circles whose powers are same. Radical axis of two circle is the location of the point, is the locus of the point whose power with respect to the two circles are equal. So we just write the small definition. Radical axis, so it is the locus. So radical axis of two circle is the locus of the point whose power with respect to both the circles are equal. Whose powers with respect to both the circles are equal. So if s1 is equal to 0 and s2 is equal to 0 are the equation of the circle, then radial axis is equation of the radial axis is s1 minus s2 equal to 0. So now if you consider the standard equation, then you are getting 2 times of g1 minus g2 plus 2 times of f1 minus f2 and plus c1 minus c2 is equal to 0. This will be the equation. Okay, now you should write the standard form and then subtract it. In figure, try to understand what is the radical axis is. In the figure, try to understand what is the radical axis. So we have one circle here and another circle we have here, okay. So now radical axis is something, if we consider the power of a point with respect to both the circles having the same. So power of a point is same. Suppose this is a P point. So now I am going to take the tangent. Okay, now, so now it will be here. Okay. So this is my tangent number 1. Now again take this value. Okay. Again take this one here. Okay. So now what you observe that if power of the point P is PA, so PA square is the power of the point, here PB square. So now this is the locus of the point P moving in such a way so that it distance, that means it is known as the length of the tangent. Square of the length of the tangent is same in both cases with respect to both the circles. So if PA square is equal to PB square, if it is happened, then we will get the above result for both the circles. So this is the equation of the radical axis. Okay, now so few interesting observation are there. So this observation we can write in this way. Few observation regarding the radical axis. So now observation number 1. So what you notice that if the two circles are intersecting, then their common chord will be the radial axis. Common chord. So if two circles are intersecting, then the common chord is the radical axis. So radical axis will be the common chord for the intersecting circle. Now observation 2, if two circles touches each other, either they will touch externally or they will touch internally, both will happen. So if it is happened, then in that case the common tangents at the point of contact, this will be the radical axis. So radical axis in this case is the tangent only. Now third case, third point, what you observe that if you have one circle, if you have another circle, now joining them, so radical axis always perpendicular. Radical axis is always perpendicular to the line joining the center of the circles. Okay, now next point is, it is not necessarily that radial axis passes through the midpoint of the line joining the C1 C2. So not necessarily not necessarily. RA radial axis passes through the midpoint, passes through the midpoint of the line segment joining the center C1 C2, midpoint of C1 C2, not necessarily. Now fifth point, what you observe that the radial axis, if you have two circle, then this is their direct common tangent. The radial axis always bisect the tangents, bisect the common tangents. Now point number 6, a radial axis, if two circles are there, they don't have any radial axis, so that means the circles are concentric. So concentric circle never have, concentric circles don't have radial axis, circles don't have radial axis. Okay, now next is point number 7. If one circle is there and another circle lies within the first circle, if one circle is here, another circle is here, not touching, entirely lies in such a way their center is not common. So one circle lies inside the other circle, one circle is lies inside the other circle, but the center are different. So in that case your radical axis lies outside of the circles. So now coming to the just go through it once again, or revision for the radical axis of the two circle. So radical axis of the two circles is nothing but the locus of the point, where the power of the points, where locus of the point where the power of the points with respect to both the circles are equal. So radical axis is actually of two circle is the locus of a point whose power with respect to both the circles are equal. So now if we consider S1 and S2 are the equation of the circle, then the radial axis is given by S1 minus S2 equal to 0. So if you consider S1 is x1 square plus y1 square plus 2g1x plus 2f1y plus c1 equal to 0, and S2 is equal to x square plus y square 2g2x plus 2f2y plus c2 equal to 0, then the radical axis equation will be 2 times of g1 minus g2 plus 2 times of f1 minus f2 plus c1 minus c2 equal to 0. Okay na? So now few observation we notice in case of the radical axis. So number one, if the two circles are intersecting, then the common chord, their common chord will be the radical axis. Number two, if the two circles touches each other externally or internally, then the radial axis will be the common tangents. But every time we notice that the radical axis is always perpendicular to the line joining the center of the circles. So but it is not passing through always the midpoint of the line segment joining the center of the circles, but it always bisect the tangents or common tangents of the two circles. And if the circles don't have, if a pair of a circle don't have any radical axis, that means the circles are the concentric. For the concentric circles there is no radical axis, they don't have any radical axis. But the circle are not concentric, one circle is lies entirely in the another circle, they do not touch each other. So in that situation their radical axis always lies outside of the circles. So these are the few points which we discuss in the point number it is what, point number 18. So this is regarding the radical axis. Now in point number 19 we should discuss some other thing, that is the orthogonality. So now we are going to discuss the orthogonality. So before describing the orthogonality, one important thing we can also discuss here regarding the radical axis. So we have a similar radical axis, we have one thing that is known as the radical center. So what is radical center? It is also important, radical center. So suppose we have the three circles and we are going to find out three circles we have, like this one, and another circle is like this one. Okay, now this one is the another circle. So third circle is there, third circle is also there. Same color is there now. Okay, wait. So now we are taking the another color, red one. So now what we have here, this one. So now what we observe that there are three circles. So if there are three circles, if you take any two at a time, if I am taking, then I am getting their radical axis. So radical axis for the first two will be here. Now the radical axis for the first and second and third will be this one, first and third, and you can say that this one radical axis for the third and the second will be this one. So what we observe that the point of intersection of the radical axis of the three circles taken two at a time is known as the radical center. So this is my circle 1, this is my circle 2, and this is my circle 3, and this is the radical center C. Okay, now so now the definition of the radical center is what? Point of intersection of radical axis of radical axis of three circles taken two at a time. So where they intersect, that point is known as the radical center. So now if I find out this radical axis, so I call this one is the RA radical axis 1. This is the radical axis 2. S1, S2, S2, S3 is radical axis 2. Then these and these will be radical axis 3. Okay, now so first I am calculating radical axis 1. So here we have 2 times of G1 minus G2, then 2 times of F1 minus F2, and plus C1 and C2 is equal to 0. Now radical axis 2, it's involve S2 S3, to 2 times of G2 G3, now plus 2 times of F2 F3, then you have C2 C3, which is equal to 0. Now RA3, so in case of RA3 we have 3 and 1, so 2 times of G3 G1 plus 2 times of F3 minus F1 plus 2 times of C3 minus C1. So first of all, these three are the equation of the lines. Where they concurrent or not, we have one property by the determinant we can check. So we consider the determinant 2 times of G1 minus G2, then 2 times of F1 minus F2, and then we have C1 minus C2. Again we have these 2 times of G2 minus G3, 2 times of F2 minus F3, and then we have F2 minus F3, C2 minus C3. This will be C2 minus C3. This will be C2 minus C3. Now next is we have 2 times of G3 minus G1, then we have 2 times of F3 minus F1, then we have C3 minus C1. So if the determinant is 0, then we can say that they are the concurrent. The three lines will intersect at the some point. So if determinant is 0, then we can say that the radical axis intersects at a some point. That means the lines are concurrent. Or another way is there. I have one mistakes is here. 2 times of G1 G2 X. Here is Y. Here is X. Here is Y. It is slightly mistake. Okay. So now you can do one thing. You can first solve the RA1 and RA2. Whatever the value of X and Y you are getting, then put in the equation 3. If it is satisfied, then you can say that they are concurrent. If it is not satisfied, then you can say that it is not a concurrent. But here it should be the case that should be the concurrent. So 3 RA1, RA2 and R3. RA1, RA2 and RA3 where they intersect, that point is known as the point of radical center. This point is known as the radical center. So now we discuss the point number 19. Now coming to the next point, which is known as the point number 20, and here we are going to describe the orthogonality. Okay, now so now we are going to describe orthogonality. Now in these points we are going to discuss about the orthogonality of the circles. So first of all, what is the definition of orthogonality? if two circle intersect or two curves intersect at 90 degree whenever they intersect. So two curves are said to be orthogonal if they intersect at 90 degree whenever they intersect. Now two curves, if they intersect at 90 degree, whenever they intersect, they always intersect at 90 degree. Intersect at 90 degree every time whenever they intersect. Whenever they intersect. So now whenever they intersect. So this is the definition of orthogonality for the two curves. Two curves are said to be orthogonal if they intersect at 90 degree whenever they intersect. Okay now. So now how can we find the angle between the two curves? So suppose this is the first curve and this one is the second curve. So in the first curve we have to draw the tangents like this one. In second curve we have to draw the tangent like this one. So here the angle, if it is 90 degree, this angle, that means angle between the two tangent is actually the angle between the two curves. Angle between the two curves is same as we consider the angle between the two tangents at the point of intersection. So when the two curve intersect at how many points? Suppose they are intersecting at the 100 points. So at every points when we measure the angle will be the 100 angle will be the 90 degree. So suppose out of 100 points, at least one point is there where the angle is not a 90 degree. We say that the curve are not orthogonal. So in case of a circle, how can we find the orthogonality conditions? So in case of a circle, we are going to find the orthogonality condition. So for this reason, I required the two circle. So first of all, I draw one circle here. This is a circle. Now take one more circle like this one, and we are going to prove that they are intersecting at 90 degree. Okay, now we want to prove they intersect at 90 degree. Okay, so now how can we prove that? So two circles are there, they have the different radius. Their equations are, we consider in this way: S1, this is my S1, this is my S1 circle, this is my S2 circle. So S1 is defined like that, x square plus y square plus 2gx plus 2fy and plus c, which is equal to 0. S2 I defined like that, x square plus y square plus 2g, here I am giving g1 f1 c1, here I am giving g2x plus 2 times of f2y plus c2 equal to 0. So now the center of the first circle, they intersect at the point here A and B, and suppose this is the center of the first circle, this is the center of the second circle. So if I join, I am getting c1 c2. Okay, now so coordinate of c1 c2 is, it is g1 minus f1, and here the coordinate is minus g2 comma minus f2. Now if I join this point, this A with C1, we are getting this AC1. So this value is nothing but R1, radius 1. Here if I joined these two, I am getting the second radius, which is equal to R2. Okay, now so now our target is, we are going to calculate the conditions for orthogonality. So we know that this angle is the 90 degree angle. So what we can apply here? Pythagoras theorem. Pythagoras theorem says that perpendicular square, so by Pythagoras we can write r1 square plus r2 square, which is equal to c1 c2 square. R1 square value we know that g1 square plus f1 square minus c. R2 square is nothing but g2 square plus f2 square minus c. Here c1, here c2. C1 C2 whole square means you have to take G1 minus G2, G1 minus G1 minus plus G2, or G1 minus G2 whole square you are taking, no problem. F1 minus F2 whole square you can take. So now if you expand it, it will be the G1 square plus G2 square minus 2 times of G1 G2, and here you have F1 square plus F2 square minus 2 times of F1 F2. So now we can see that few terms get cancelled. So first of all, G1 F1, G2 F2, from here G1 F1, then G2 F2 cancel out, and next is what? C1 C2 only left. So now I am taking here 2 times of G1 G2 plus 2 times of f1 f2, which is equal to c1 plus c2. So if I take 2 common, it will be 2 times of g1 g2 plus f1 f2 is equal to c1 plus c2. So this is one of the very important formula. This is so much important that every time it may happen that one question in JEE mains you have to apply this formula. Okay na? So this is the condition for orthogonality of the two circle, where the two circles intersect at 90 degree. So these conditions hold. 2 times of g1 plus g2, 2 times of g1 g2 plus f1 f2 is equal to c1 plus c2. So g1 g2, you know that these are the x coordinate of the center of the circle, है ना, and f1 f2 y coordinate of the center of the circle. So 2 times of g1 g2 plus f1 f2 and is equal to c1 plus c2. 2 times of g1 g2 plus f1 f2 is equal to c1 plus c2. So now in this point number 20, what I am discussing, orthogonality. So two curves are said to be orthogonal if they intersect at 90 degree whenever they intersect. So in case of a circle, we are going to find out the condition when they intersect at 90 degree angle. So in that situation, what is the criteria when we say that the two circles are at 90 degree, intersect at 90 degree? So first of all, at their point of intersection, if you draw the two tangents, the two tangents having the angle between them is 90 degree. So two tangent having the at the point of intersection, if two tangent having the 90 degree angle between them, it is same as the true curve having the 90 degree between them. So we say that we call it is a orthogonal curve. And now how can we find the conditions? So we apply here Pythagoras theorem, radius square plus radius square equal to the distance between the two center square. So from here we are getting the condition 2 times of g1 g2 plus f1 f2 is equal to c1 plus c2. Okay na? So now we are moving to the last part of this topic, that is called pole and polar, and that will be the point number 21. So now coming to the point number 21, where we are going to discuss about the pole and polar. These things we are going to discuss, pole and polar. Now what is pole and polar? Suppose in the plane of a circle we take a point P. So in a plane of a circle, so this is my circle and I am taking one point P here. Okay na? And through the point P I can draw any line which intersects. So any line through the point P intersect the circle. Any line through the point P intersect the circle at 2 points. Any line through the point P intersect the circle 2 points at 2 points, like this one. Okay na? Now if they intersect at the circle at the point, suppose they intersect at a1 b1, here they intersect at a2 b2. Okay na? So now our target is we are going to draw the tangents at the point a1 b1. So at the point a1 and b1 we are going to draw the tangents. So now if you draw the tangents here, you notice that the tangent will be look like this. But you notice that tangents will be. So now if you are going to draw the tangents, here, so these will be our tangents, like, yes. So I am getting the tangents at the point A. Now next is we have to draw the tangent at the point B1. So at the point B1 we are going to draw the tangents from here, like this. Now if you extend this one, so they will intersect at this point. And this point I am calling as C1. Now again draw the tangent at the point A2. So this will be the A2. Draw the tangent here. Draw the tangent at the point A2 and draw one more tangents at the point. At the points B2. Draw one more tangents at the point B2. this one. So now if you draw the tangents, what you observe that they will intersect at some point. This point I call C2 point, this point I called C2 point. Okay, now so there will be slightly change here. Okay, now there will be slightly change here. These will be like, these will be like this one, these will be like, so suppose they intersect at the point C2. So now when we join C1 and C2, we are getting the one straight line. When we are joining the C1 and C2, when we are joining C1 and C2, we are getting one straight line like this. Okay, wait, we have to change the color. Now I am going to use here another color, green color. Okay, now so now from here we get, from here we are getting this value. So if you joined, what happened actually I don't know. So we are getting the straight line, actually we are getting here straight line. Okay, now so now this green color line is called the actually polar, sorry, this green color line is called the polar, and this is known as the pole. Okay, now so what is the definition of pole and polar? In the plane of a circle, we take any point P, and through the point P we draw any line which intersect our circle at the 2 point, and that 2 points we are drawing the tangents. Now the tangents intersect at some point, so we are joining the intersection point. That means locus of the tangents, locus of the intersecting tangent, locus of the intersecting tangent is known as the polar. Locus of the intersecting tangents, locus of the intersecting tangents are known as the, locus of the intersecting tangents are known as the polar of the point P with respect to the given circle. So now for example, if I am taking point x1 comma y1, this point I am taking, and my equation of the circle is x square plus y square equal to a square. So we can say that the equation of the polar will be x into x1 plus y into y1 is equal to a square. For the general equation GE, if I have the equation of the circle like this one, x square plus y square plus 2gx plus 2fy plus c is equal to 0, then we can say that the polar equations will be, equation of the polar will be xx1 plus yy1 and g of x plus x1 plus f of y plus y1 and plus c equal to 0. So this is the equation of the polar with respect to the pole, with respect to the pole x1 y1. Okay, so now depending upon the position of the point P, we have the different pole and polar. So first of all, consider case 1 where P lies outside of the circle. So we have one circle and P lies outside of the circle. So if P lies outside of the circle, suppose here, then what will happen? We should draw one line through the point P, then we will get the tangents here like that. Again from the point P we should draw another line which intersect our circle like this and this. Okay, now so here and here if you draw the tangent, so just previous diagram we will obtain. Our polar lies inside the circle. Okay, now so in this case what we observe that this will be the tangent here, here one tangent intersect, two tangents we are drawing, and in the below part we have again two tangents like this one and this one. Okay, now so these 2 points we have to connect, these 2 points we have to connect, and we are getting the polar. So if P is lies outside, then the polar will be this one. So this is our polar. It may happen that the point P lies inside the circle, it is happened. So in that case, if I have the circle like this one and the point P x1 y1 suppose lies here. So P x1 y1 lies here, okay na, inside the circle. So if it is inside the circle, like this is my point P, so I should draw the line segment which intersect the circle at the, suppose A and B. Another line segment I am taking which intersect the circle at the points C and D. So our target is we have to draw the tangents at the point A and B, at the point C and D. We have to draw the tangents. So at the point C, if I draw, my tangents will be look like this. In this way we are getting the tangents. At the point B, if I am drawing, the tangents will be look like this. So I think it is very bigger circle, so it is very difficult to draw or show. I am taking a smaller circle so that I can show you what actually happened. Okay, now. So now I am taking one smaller circle like this one, and here is the point P. Here is the point P, and suppose this is the line which I draw through the point P, through the point P. So now in this case, from here we have to draw the one circle, one tangent, sorry. So this will be the tangent. Now from this point we have to draw the tangent, they will intersect here. Now here I have to draw the tangents at this point and also this point. So you notice that here we get the intersection, here we'll get the intersection. So if I join these two intersection, we will get the polar, we will get the polar. So this will be the polar and this point will be the pole. Third cases may happen that when the point is on the exactly circle. So what will happen in that case? Suppose now it is our circle, okay, and we have the point is here, we have the point is here, P point. So if the point is here, P point, then what will happen? This is our x1 y1 point, x1 y1 point. So through this point you have to draw the line which intersect your green line at 2 points. So suppose if you are taking like this one, I am taking this one, okay. Now next I am taking this one, okay. So now if you draw the tangent at this point, what will happen? So tangent at this point look like this one, okay. And now if you draw the tangent here at this point, it will be look like this. Okay, now if I draw the tangents at the point P, then what will happen? Okay, now wait, yes. So what you observe that now this is the point, this is the tangent 1, tangent 2 intersect here, here the tangent 1, tangent 2 intersect here. So if you draw, then you will get the tangent actually. So now when the point P lies on the circle, then in that case tangent at P x1 y1, number 1, number 2 polar at x1 y1, and you can say that chord of contact, COC, chord of contact through the point P x1 y1 is all are same. So when the point is on the circle, then the polar, then the tangent and the chord of contact are nothing but the same straight line. So now we just go through this again. Point number 21. So pole and polar. What is pole and polar? So in the plane of a circle, you have to choose one point. Through this point you have to draw the lines which intersect your circle at 2 points. That 2 points, on these 2 points or through these 2 points you have to draw the tangents. Tangents will intersect at some point. If you joined all the intersection point of the tangents, then you will get a straight line. This line is known as the polar with respect to the given point P, and P is called the pole of the polar. Now the different situation appears when the P point is lies outside of the circle, P point is lies inside the circle, P point is on the circle. Then the different pole and polar we have. So now in this video classes I am describing, I'm trying to describe all the theories here. Not any problem, but in the next lecture that will be the very lengthy, because all the questions, different types of questions I have to going to discuss there. So in theory part, if you have any doubt or some point I have missed, please text me in the inbox, so that in the next video I will cover it. And if there is anything which is not suitable or which is wrong, you can point it out me, no problem. Now thanks for watching the Maths Academy, and thanks very much, and thank you so much to attach with me. Now we will meet in the next video. Till then, bye, have a nice day.